Hello viewers, you're welcome to SciX tutorial, and in today's video we'll be diving into a powerful tool in calculus, which is how to evaluate limits of a function by using the squeeze theorem. So today we'll be considering points like: number one, what is squeeze theorem? What is squeeze theorem? What does it say? Number two, when do we use squeeze theorem? When do we use squeeze theorem? The next is when not to use it. When not to use the squeeze theorem. And the next is squeeze theorem always zero? Is squeeze theorem always zero? And lastly, we'll look at examples of how we evaluate limits using the squeeze theorem. So, to point one, what is squeeze theorem? So squeeze theorem is a very powerful tool in calculus. We use it to evaluate the limits of functions. And what does it say? It says that when we have a function, say f of x, such that when we have a function, say f of x, such that f of x lies in between two other functions in such a way that the limit of g of x and the limit of h of x as it approaches a particular variable, if these limits are equal, then we can actually say that the limit of f of x is actually equal to either of them. And of course, since the two of them are equal, then we can say that the limit of f of x approaching the same value as each of them is equal. So what we are saying in essence is, for example, if the limit of h of x as x approaches a is equal to L, and the limit as x approaches a for g of x is equal to L, then we can actually say that also the limit of f of x as x approaches a also equals to L. But you agree with me that it's very difficult to know what the limit of f of x is in the original sense, because f of x in many cases, which is the reason why we are using the squeeze theorem, in many cases it's an oscillating function. You just cannot tell what's happening to it, right? So this is the squeeze theorem. Then when do we use the squeeze theorem? A very important question to look at. The squeeze theorem is used when we are dealing with oscillating functions, when we are dealing with functions that we cannot get using direct substitution, functions we cannot get using either simplification method by factorizing or rationalizing, functions that we cannot get using L'Hopital rule, that means by differentiation, right? And if any of these indeterminates show up, and then we know that those functions are oscillating, then it's squeeze theorem that we use. So we'll now see when not to use the squeeze theorem, provided even if squeeze theorem can handle any question. If that function is not oscillating, then don't use squeeze theorem, because you might actually end up with a different value like what the other algebraic methods can give to you. So don't use squeeze theorem. Secondly, squeeze theorem is not supposed to be used, or is not used, when the function is oscillating but cannot be bounded. If you cannot bound that function, then you cannot use squeeze theorem. Like what we have on the board, right? This f of x that we are interested in is actually bounded in between two functions, h of x and g of x. That's why it's called squeeze. You're trapping it. You're trapping the function. You're squeezing it in between in between two other functions. So we've answered when not to use the squeeze theorem. Now, how do we evaluate limits using the squeeze theorem? So that's what we'll be looking at, and that's what we are more of our time will be dedicated to. Okay, so I'm going to rub out the first three. Of course, by now you've seen what my questions are, so I'm going to take every one of them off. Remember what we are dealing with right now, how to evaluate using the squeeze theorem. So we'll be looking at the following questions. The limit as x approaches 0 for x sine 1 all over x. Number 2, the limit as x approaches infinity, sine of x divided by x. Number 3, the limit as x approaches 0, the square root of x e raised to the power of sine 1 over x. And lastly, number 4, which will be an exercise question. So number 4 will be an exercise question for us. You can attempt it and leave the answer at the comment section. So you have the limit for x approaches 0 for x squared cos 10x. So these are the questions we'll be looking at. Let's dive to see what number 1 would be. So for this function is actually an oscillating function, but can we bound it in between two functions? Let's see. First, we have sine of 1 all over x, and we know that there's the range of sine of any degree is within the range of 1 and -1. The range of sine of any degree is in between -1 and 1. So that's the range. So we've been able to bound this function in between -1 and 1, right? Okay. So but the function we are dealing with says x sine of 1 over x, right? So what we are going to do to both sides is that we are going to multiply both sides by -x, right? We are going to multiply all through by x rather, so that we can get the function we are dealing with. So if you multiply through by x, you get -x is less or equal to x sine of 1 over x less or equal to x. True? Okay, take the limits of both sides. Take the limits. Our limit of x approaches what? 0. So for anywhere you see x, you put 0. So this becomes 0. Of course, there is nothing like -0, so it's still 0. So 0 is less or equal to x sine 1 over x less or equal to 0. So we've been able to find the limit of the two functions that we trapped our function in between. And remember what the squeeze theorem says: if we can get the limit of those two functions, then our function, the limit of our function is actually that value, right? So it means therefore the limit as x approaches 0 for x sine of 1 all over x is equal to 0. It's as easy as that. But you agree with me that something like this, the L'Hopital rule cannot handle it, because this function is a function that is oscillating, right? So we'll keep using the squeeze theorem to attempt question of this nature. Now let's see the next question. For question number 2, we have the limit for x approaches infinity, sine x all over x, right? This also is an oscillating function. This function is unbounded. Actually, this is an unbounded function, so you cannot get the limit with any of those algebraic method. It's very unbounded for x approaches infinity. That's why we want to see if we can be able to bound it in between anything we know, right? In between any two other functions that we know. Let's see if it's possible. We are dealing with sine again, so we know that the range of sine, we can bound sine So sine of x is less or equal to 1 minus 1. Is that true? Yes. So now our function says sine x divided by x. So what do you think we are going to do so that we can get exactly our function in between those two new values we've gotten? Yes, you're right. So we are going to be dividing all through by x. So if you divide all through by x, you have minus 1 over x is less or equal to sine x divided by x, which is less or equal to 1 over x, right? So I'm going to be cleaning this part of the board. I'm going to be cleaning the previous solution so that we can have space to do what we are dealing with. Okay, still keep in mind of what we have. Negative 1 over x is less or equal to sine x divided by x, which is less or equal to 1 over x. So at this point, we can take the limit of the function for x approaching infinity, which is our question. So if x approaches infinity, we have negative 1 divided by infinity is less or equal to sine x over x, which is less or equal to 1 divided by infinity. Of course, negative 1 divided by infinity is 0. So 0 is less or equal to sine x divided by x, which is less than 1 over infinity is 0. So we've been able to get two functions, two values that we bound our function in between. So it means that the limit, therefore the limit as x approaches infinity for sine x divided by x is equal to 0, right? So for the last question, I'll be dealing with question number 3 for us, but we'll do number 4 as an exercise. Okay, for question number 3, please, if you don't understand, you can leave your questions on the comment section and it will surely be attended to. So for question number 3, which is the last question I'll be dealing with, the limit as x approaches 0 for square root of x e raised to the power of sine of 1 over x. We have sine of 1 over x, which was actually what we started with from our question number 1. We can start there. Okay, so we have sine of 1 over x. This is bounded between 1 and negative 1, right? So the next thing is what are we going to do? We are going to take the exponential of this function. We are going to raise this function with e, right? So this is e raised to the power of negative 1 of less or equal to e raised to the power of sine 1 over x, which is less or equal to e raised to the power of 1, which is the same thing as e. Okay, we've not been able to get the same function as what we had or as what we are dealing with. So the next thing to do is to multiply by the square root of x. The next thing to do is to multiply by the square root of x. Okay, and I'm going to clean this part of the board, the previous solution. Okay, so we'll be multiplying this by the square root of x so that we can get our function bounded in between the left and the right. So if we multiply by square root of x, you get square root of x e raised to the power of negative 1 is less or equal to square root of x e raised to the power of sine of 1 over x less or equal to, okay, it's not enough. So I have it as the square root of x e raised to the power of negative 1 is less or equal to square root of x e raised to the power of sine of 1 over x less or equal to e raised to the power square root of x e. So we've been able to get our function, right, bounded in between these two values, these two functions. So at this point, what do? We'll take the limits for x approaching what? 0, because that's what x approaches in our question. So if x approaches 0, square root of 0 is the same thing as 0, and if you multiply this with 0, you still get 0. So 0 is less or equal to square root of x e raised to the power of sine of 1 over x, the limit of sine, which is less or equal to 0. Okay, so therefore we can now say at this point now that the limit of x approaches 0 for the square root of x e raised to the power of sine of 1 over x is equal to 0, because we have 0 on both sides. So since it's bounded in between two values, then the limit of that function is actually that value, right? So we've been able to see how to evaluate the limits of function using the Squeeze theorem. You will do this as an exercise, like I said earlier, but let's look at the last point, which is the limit, or is Squeeze theorem always 0? For the three questions I solved, I actually arrived at 0. So somebody might be asking, is it that Squeeze theorem is always 0? No, it's just depending on the function you're dealing with. There are functions that you use the Squeeze theorem on and you don't get a 0. For example, I leave you with this. You can try it and tell me what you get in the comment section. The limit as x approaches 0 for pi plus x sine of 1 over x. So you can tell me what is your result, what you get at the end, and see if the limit or the Squeeze theorem will always give us 0 as an answer. So up until I come to your way next time, don't forget to like, subscribe, and hit the notification button so that when next videos are uploaded, you will see. Thank you.